Alright, week 6, problem 12. Values of the components in a simple series RC circuit containing a switch and an initially uncharged capacitor. See figure below. Capacitance equals 1 microfarad, resistance is 2.5 mega ohms, and the battery is 5 volts. Alright, so the charge on the capacitor a long time after the switch is closed. Okay, so whenever I start doing capacitor problems, I pretty much always draw a picture. And pictures, it's like one of 3 different types of pictures. So start like this. So a long time after, so I'm going to say this is Q, I'm going to say this is time, and it's going to build up like this. So I know that charge is going to build up. So I'm basically like, alright, is the charge going to build up like this, or is it going to build up like this? Well, building up like this doesn't really make sense, because then after time the charge would get exponentially huge, and then you infinity, and infinity is pretty big for a amount of charge on a capacitor. So this one makes more sense because it kind of finds a maximum charge that can be on a capacitor, and it levels off of that. So we know that capacitance equals Q over V. So what we're going to have then is the total charge at time t equals infinity is going to be let's see here. We'll say that V equals Q over C. No, that's not useful to me at all. I want to find charge. Q equals CV. There we go. Q equals CV, which we know that capacitance is 1 times 10 to the negative 6. 1 times 10 to the negative 6. Okay? And then we also know that voltage is 10. So charge will equal 10 times 10 to the negative 6. There we go. That's pretty straightforward. So it'll be 10 microcoulombs. So this will be 10 microcoulombs. That's poorly drawn. Draw a nice micro. Oop, there we go. And the coulomb. There we go. Better. Alright, so now we need to know what Q is after the switch is closed. 3.6 seconds. Alright, so for this, we're going to have to make an equation. And they give us equations. But I always try and just kind of reinvent the wheel every single time. So I'm going to say it's e to the negative t over RC. There we go. Negative t over RC. Alright, so there's 2 equations. There's this equation, and then there's this equation. 1 minus e to negative t over RC. I can never remember which one goes where, so what happens is I just write one up and I plug in 0 or infinity and make sure it's right. So for this guy, when e to the negative infinity over RC, RC is a constant, it's a time constant, I think, tau is what they use, and so it's not going to go to infinity because it's a constant, but t can go to infinity. So e to the negative infinity is 1 over e to the infinity, which is 1 over infinity, so it's 0. So this right here would then e to the negative infinity, so this one would go to 0. So this says at time infinity goes to 0. So this equation actually applies to a picture that looks like this, which is a discharging capacitor. Alright, so now for this guy, alright, so this guy, e to the negative infinity over RC is 1 over e to the infinity, which is 0. So at infinity, it'll be 1 minus 0. So all that will be left will be Q naught. So yes, this is the equation that we want to use right here, because it matches the graph that we want to have. Okay, got it. So now we need to do 3.6 seconds. So I just remember that you have the R and C together. For capacitors you have RC, That's the time constant. For inductors, which you'll learn about later, you have R over L. So just remember negative T over RC. Okay, so then we're going to have 10 microcoulombs, which is what we're going to start with for our initial. We're going to 1 minus E. Now we need to do some math. So it'll be negative 3.6 over R, which is something huge, wasn't it? 2.5 times 10 to the 6th. So we have, I'm just going to solve RC up here. So RC equals 2.5 times 10 to the 6th times 1 times 10 to the negative 6. Cancel, cancel, equals 2.5. Okay? And I think that's actually measured in seconds. $2.5. I'm going to put this into Wolfram and see if it gives me a reasonable answer. So 10 times quantity 1 minus E to the negative 3.6 divided by 2.5. So and I get 7.632. It seems reasonable. Yeah, I might use 7.632, and this will be microcoulombs. So what happened is, I'm going to say this is right here. This is 3.6 seconds, and we are now at this part of the graph right there, which is 7.6. Oh, there we go. So here we have 7.62. Excellent. So we charged for a while. So now we have the current in the resistor immediately after the switch is closed. Okay, so this is where you use the hydraulic analogy. Immediately, so a hydraulic analogy says that the capacitor acts like a diaphragm. So when you have your diaphragm, you have water push against it, it's going to immediately push forward and push the water on the other side. So to do that in picture form, you have a pipe, you have your diaphragm, water pushes this way, it pushes the diaphragm that way, the diaphragm then pushes the water on the other side, and immediately when it's zero stretchiness to some stretchiness, it's not going to offer any resistance and it push the water straight to the other side. Eventually the diaphragm will become fully stretched, and this water will be just used to keep the diaphragm stretched, and it won't actually push any more water through the other side. So the way you model a capacitor at time t equals 0 is as a straight wire. So immediately after the switch is closed, so initially uncharged. So immediately after the switch is closed, we model this as a wire, and we just find the current through the resistor as normal. So we have what? Is it 10 volts? 10 volts. 10 volts and 2.5? 2.5 megohms. So we just do V equals IR here. So V equals IR, which tells us that I equals V over R, which means that V is, I should know this, 10 over 2.5 times 10 to the negative 6th times 10 to the 6th, which equals 10 divided by 2.5 is 4, and then this will be microamps. So this will be 4 microamps. Excellent. Now 3.6 seconds after the switch is closed. Okay. So 3.6 seconds after the switch is closed, we're going to have 7.62 microcoulombs. Okay. So I'm going to draw another graph. Same idea as before. So current is going to act very similar to charge. So that's going to be time. This is going to be current. It's going to start at a maximum, which we know is when it just started, which is 4 microamps, and it's going to decay. And it's going to decay using the same equation that we wrote up here. Except this time it's going to be I will equal, at any given time, will equal initial current, the maximum current, times e to the negative t over RC. Okay? So this time, 3.6 seconds, we're now going to use this equation. And just to make sure it makes sense, as t goes to infinity, it goes e to the negative infinity, which is the same as 1 over e to the infinity, which is the same as 1 over infinity, which is 0. So that makes sense. That equation makes sense. Alright, so I'm going to jump on this bandwagon here. So we have, instead of 10, we're going to have 4. We're going to get rid of the 1 and the minus. And everything else is going to be the same. And that's going to give us 0.97. 0.95. Okay. I believe that, 0.95. So current is decreased to about a quarter of what it was. So in a long time after the switch is closed, the diaphragm is going to be fully stretched, so there'll be no more movement. And one way to look at it is at infinity, you can model a capacitor as an open, as if no wire there. Initially you model it as a wire, then you model it as nothing, no wire. So there will be no current going through the resistor at time t equals infinity. Alright, now we need the rate at which energy 3.6 seconds after the switch is closed is being dissipated in the resistor. So for resistors, I use P equals I squared R. Alright, so then, right, there we go. P equals I squared R squared. That's a terrible square. What are you doing, little pen? Alright. There we go. There we go. Alright, so at 3.6 seconds we know we have 0.95 microamps. So the rate at which it's being, the rate, which is power. The rate at which energy is used as power. So we will do, so this will be 0.95. This will be, equals 0.95 squared, and then we'll have 10 to the negative 6 times 10 to the negative 6. And then we're going to multiply by, because that's 10 to the negative 6 squared. Then we'll multiply by the resistor, which is 2.5 times 10 to the 6th, which will get rid of one of our 10 to the 6th. So what we're going to have then, right, we can do this. So we'll do 0.95 squared. 0.95 squared times 2.5. Yep. Times 2.5. There we go, and we get 2.26. All right. 2.26. Excellent. So now we have rate at which energy is being stored in the capacitor. Okay, so we're just going to do the same idea. So power for a capacitor. Okay, so if I find interesting. So we have power going out of the battery. Then we should have rate at which energy being dissipated by the resistor. So let's see, the voltage. Okay. So what I'm going to do here then is I'm going to use our equation P equals IV. So power equals IV. Now the voltage for a capacitor over time is going to change. So it's going to start, it initially acts as a short, and then eventually it's going to act as an open. So the voltage of a capacitor is going to climb like so. So we're going to use the same equation that we used earlier with the 1 minus involved. So we're going to do our initial voltage, which is our maximum voltage, I guess, which would be, nope, that's not what I meant to do. There we go. V equals V naught times 1 minus E to the negative TC minus E to the, there we go, T over RC. So the maximum voltage we're going to have is at the end. So the way to think about this is the voltage drop across the resistor is going to be V equals IR. Well, at the end, in the beginning there's going to be a lot of current going through the circuit, but at the end there's going to be no current flow. Therefore, there's going to be no drop in voltage across the resistor. So we have no voltage drop across the resistor, all the voltage drop will then happen across the capacitor. So the maximum voltage drop we will have is going to be the full voltage, which will be 10. So this guy right there is going to be 10. Alright, so now I'm going to plug everything in the way we had it. Let's see, RC is 2.5, so 3.6 divided by 2.5. So we're going to have 10 times 1 minus E to the negative 3.6 divided by 2.5. That probably works. We'll see. And that gives us 7.6. That's believable. So, because voltage is rising. So this is going to be .95, which is what we determined already to be the current flowing through the resistor. And the current flowing through the resistor is going to be the same as the current flowing through the capacitor because they're in series. So 0.95 times 7.6. 7.63 just to, alright, and I'm going to open up another link just to save the data I have. 0.95, 0.95 times 7.63, and then we're going to get 7.25. Now at this point I've completely lost where the units are supposed to be. I think there's supposed to be a micro there, so micro times normal volts. So I'm going to say that we have 7.25. So power being delivered by the battery. So conservation of energy, if we're losing 2.26 due to I square R losses and we're storing 7.25 microwatts in the capacitor, then we add the two together. I'm going to pretend it's 0.25. We're doing 9.50 microwatts of power being delivered by the battery. Alright. Yep, and that is it for this guy. So the key takeaway here is every time I think about capacitor, voltage, current, I draw a picture. Either the graph goes up or the graph goes down. I then write out the equation. There's only going to be two equations. It's either going to be this one or this one. And I just guess and check which one's right. Sometimes I'm right, sometimes I'm wrong. But that's where you guess and check. If it turns out you're wrong, you just choose the other one. Not a big deal. Alright, and that's how you should think about capacitors and simple RC circuits. Perfect. Alright, see you on